Dear students, today I have to discuss a very simple and fundamental part of the chemistry, that is oxidation number. That oxidation number, will help to get idea about the equivalent weight, to get correct idea, actual concept of equivalent weight with respect to redox reaction. Oxidation number is important. And in a chemical reaction, mainly in redox reaction, which atom of molecule oxidizes or which atom of molecule reduces, that idea you will get from the oxidation number counting. Moreover, remember, to get a preliminary idea of an inorganic reaction, an inorganic redox reaction, oxidation number will help you to predict about the nature of the reaction. That's why oxidation number of an atom in molecule is an important part of our fundamental chemistry. I'm going to discuss what is oxidation number. Actually, remember, let a bond A, B. Since A and B are different atom, their electronegativity different, must be different. And the bond is not purely covalent. If I do consider it is purely covalent, their electron cloud, if I take orbital or electron cloud concept, their electron cloud should symmetrically distributed among the two nucleus A and B. If I take it as a dot vertical nature, then this dot should reside just middle of the two nucleus. One electron from A, another electron from B. Then it is purely covalent. But here A and B different. Their effective nuclear charge different. Their electronegativity different. Never this electron pair will reside just middle of the nucleus. It I consider A be more electronegative than A. Then the actual position of electron polarized towards the B from A. Electron pair or electron cloud polarized from nucleus A to B. That is the real position. That means this will get partially negative, this will get partially positive. Actually, oxidation number will give qualitative idea of polarization of electron. Focus on the term, qualitative idea of polarization of electron. See how. This is the middle. An electron of B goes towards the B, it has no problem. But electron of A also goes towards the B. Since this electron of A crosses the boundary, middle boundary, one electron cross, that's why it is -1, and it will get +1 oxidation number. What I told you, it will give qualitative idea of polarization of electron. That means what amount of electron cloud polarize, that idea you will not get from oxidation number. That idea you will get from the dipole moment measurement. Here oxidation number will tell you the significance of sign is the direction of polarization. Significance of sign. Sign will tell you direction of electron polarization. Electron will polarize from plus to minus. And this 1 has significance, low quantitative significance of what? Actually, 1 is the number of electron polarization. How much electron polarized, that idea everybody will get from the oxidation number. I told you that you will get from dipole moment. That means simply you can say for a bond, one bond, this is one bond. Electronegative atom will get -1 oxidation number. electropositive will get +1 oxidation number. And when the electronegativities are same, the electron clouds are symmetrically distributed, or you can say the electron pair just middle of the two nucleus. That means the oxidation number of both atoms is 0. For example, if both are A2 molecule like N2O2H2, then it is a purely covalent. Electrons are just middle of the two nucleus and oxidation number both are 0. Even part is 1. When there are similar atoms, for a bond, both will get a 0 oxidation number. For different atom, electronegative will get -1, electropositive will get +1 oxidation number. That means to get the correct oxidation state or oxidation number of an atom in a molecule, you have to know the structure of the molecule. Actually, we have a preliminary concept. There we will do calculate the average oxidation number of an atom by considering fixed oxidation state of other. Like generally we will take hydrogen +1, oxygen will take -2, halogen will take -1, alkali metals +1 always, alkali earth metal +2 always. That is different. That you will, from that you will get average oxidation number idea. But exactly the oxidation number of a particular atom in a molecule correctly you will get if you know the structure of the molecule. And structure idea you will get in chemical bonding chapter. We have different inorganic chapter, T block elements, D and F block elements, cohesive compound. From there you will get enough idea about the structure. Don't worry about the structure. Now, I'm going to give an example. You know water molecule? The structure of water molecule, this one. How big you will get the oxidation number of a particular molecule that I am showing. You know, for this code, hydrogen, you know, electropositive +1. And I told you, electronegative oxygen, we get -1. For this bond, again it is -1, it is +1. That means the oxidation number of oxygen in water, that is -2. This is +1, this is +1, and total is 0 since water is a neutral molecule. So simply you got, by very simple way, you got the oxidation number of different atoms in a molecule. But the condition is you have to know the structure. I'm going to give another example. You know hydrogen peroxide. Hydrogen peroxide, this is the structure of hydrogen peroxide. Now, for this bond, you know, hydrogen is electropositive +1, oxygen is electronegative -1, and hydrogen here electropositive +1, oxygen is -1. And for this bond, I told you, since their electronegativities are same, these are 0, 0. That means you got the oxidation number of oxygen in peroxide, that is -1. Don't you have to remember? If you know the structure easily, you will get the oxidation number of different atom in molecule. In peroxide, oxygen is -1 oxidation number. If I take another molecule, for example, F2O, area fluorine oxide. You know fluorine is more electronegative than oxygen. That's why it is -1, it is +O. This is -1, this is +O. That means here the oxidation state is +2, here -1, here -1. If you know the structure, you will get the oxidation number. I give some critical structure. From where you will get the oxidation number of different atoms. See my example? Simple structure if I take like H2SO4, C H2SO4. This is the structure of H2SO4. Now, for this bond, there are two number of bond. Oxygen is electronegative -2, sulfur here +2. For here also -2, this is +2. Here oxygen is -1, -1, it is plus. This is -1, plus. And for oxygen here also another -1 due to this bond, another -1 due to bond with hydrogen. Hydrogen here +1, hydrogen here plus. So total oxidation number of the sulfur in sulfuric acid you got +6. Also by counting hydrogen taking +1, oxygen taking -2, you will get also +6. But if the structure is somehow different, then that calculation will not match with the actual oxidation number if the structure is slightly critical. That example I'll show you. Here sulfur is +6 oxidation number or oxidation state. One thing I want to mention here, the oxidation number, actually minimum oxidation number and maximum oxidation number you can predict from the isolated atomic structure. For example, nitrogen, if I take example of nitrogen. Nitrogen has halox electron 5. Maximum it can take 3 electron. That's why its minimum oxidation number -3 that you will get in ammonia. Whereas maximum 5 electron can polarize with the other or more electronegative atom like oxygen or fluorine. If all 5 valence electron will polarize towards the oxygen like or more electronegative atom, then the oxidation number of nitrogen maximum +5 that you will get in HNO3 or NO3 minus radical. And nitrogen minimum oxidation number -3, maximum oxidation number of nitrogen in molecule +5. And in all molecule of nitrogen, there you will get minus in between -3 to +5. Similarly, sulfur, there are valence electron 6. It can accept maximum 2 electron, minimum -2, maximum 6 electron may polarize towards the more electronegative like oxygen, +6. That's why in any sulfur compound, the oxidation number of sulfur in between -2 and +6. And in the next part of the video or classes, I'll discuss from the oxidation number how you can predict the teacher of redox reaction. That is another part of the class. Now, here I am going to discuss oxidation number, how you will get from the structure. Now I will take some critical structure like thiosulfate. Thiosulfate H2O3 2-. Here the oxidation number of sulfur. If I do count by simple way, that is by taking oxygen with -2 and sulfur, if you take X, then 2X -3 into 2, -2 for oxygen is equal to -2. That you will get X is equal to +4 by 2, that equals to +2. Now sulfur oxidation state here +2, but remember this +2 is the average oxidation number of sulfur. Here 2 number of sulfur atom, and that 2 sulfur atoms has different oxidation number that only you will get if you are able to draw the structure. If I draw the structure of thiosulfate, actually it is you can draw it is from the sulfate. You know the structure of sulfate. This is the sulfate radical structure. If you can replace one oxygen by sulfur, then you will get the thiosulfate structure. You can replace this oxygen. If I do replace this oxygen, this is thiosulfate H2O3 2-. You can replace double bonded oxygen like this one. This is O-, O-. This is double bond S, double bond O. But remember, this is rock structure. Since sulfur never make any pi bond. Since 3p pi bond is very weak, never they form any pi bond. Actually, if I take S double bond S structure, then you will get 2 different sulfur in thiosulfate, one with +4 oxidation state, another sulfur you will get with 0 oxidation state. But in thiosulfate actual, there are one sulfur with +5, another sulfur with -1 oxidation number. Then what I will write here? I'll write here coordinate bond. Actually, one sulfur is donor, another sulfur is acceptor. You can write this one plus and minus. Never S double bond S you will get in any compound. Now draw what is the oxidation number of 2 different sulfur individually. That was average. This +2 was average. See, for this bond +1, for this +2, plus 2. That means plus 5 for this, since both are sulfur 0. That's why plus 5. Yeah, plus. And this sulfur, this is 0, already there are minus 1. That means minus 1. In thiosulfate, there are two number of sulfur atom and their individual oxidation numbers are different. One with plus 5, another with minus 1. And total is plus 4, and if you do average, you will get plus 2. Although in stoichiometry, average oxidation number is important, but if a question will come, what is the individual oxidation number of sulfur in thiosulfate, there you have to write plus 5 and minus 1. If you take this structure, also there you will get plus 5 minus 1. For this plus 1, plus 2, plus 3, plus 4, and already there is a plus, that's why plus 5, and it will be minus 1. But in both structure, the two different sulfur, A thiosulfate, one with plus 5 oxidation state, another one is minus 1 oxidation state. Okay. Now, you got an idea how you will get the oxidation number of different atom in a molecule. Now I take another example. Where you will get the oxidation number of different molecule. Na2 S4 O6. This is sodium tetrathione. If I do calculate, then average oxidation number of the sulfur, this sulfur, sodium is plus 1. Do it to plus 1. Sulfur you don't know. 4x plus 6 into minus 2 is equal to 0. Molecule is neutral. And from there, if you do calculate, x is equal to plus 2.5. You got fraction. But go to my definition. Oxidation number will define the qualitative idea about the polarization of electron. If it is number of electron polarization, then it never be fraction. But here you got fraction due to average of 4 different sulfur oxidation number. Actually, if you draw the structure and if you do calculate the 4 different sulfur atoms oxidation number, never you will get fraction. See the structure and see the medic how you will get the oxidation number of different sulfur in sodium tetrathione. This is the structure of sodium tetrathione that we will get in P block. This is sodium tetrathione, Na+. Now, see, more electronegative oxygen oxygen more electronegative than sulfur. It will be how many bonds with more electronegative sulfur? 1, 2, 3, 4, 5. And for this bond is 0 since both are sulfur. This is plus 5. And this is 0, this is 0, this is 0. Here this sulfur with 0 oxidation state. This sulfur also with 0 oxidation state. This is plus 5. 5 number of bond with oxygen. Now total 10, and if you do average divided by 4, that's why there you got plus 2.5. Plus 2.5. That means simply, very simply, easily you will get the oxidation number of different atom if you know the structure of the molecule. If you know the structure of the molecule. Now, I'll take another example. CrO5, that is blue color, unstable, CrO5. Actually, it should written as CrO2 whole 2O. Actually, O2. Somewhere, O2 written. That may be peroxide or superoxide. Remember, this is normal oxide. Here, chromium, if you take oxygen is minus 2, then you will get plus 10. But it is impossible. Never you will get plus 10. Since you know chromium valence number of electron is 6, its maximum oxidation state plus 6, never greater than plus 6. But if you take oxygen minus 2, here you will get plus 10. It is impossible. That means there you have to go the structure. All oxygen are not in minus 2 state. How you will get? If the formula given like this, then I take O2 2 minus, that are peroxide. But the structure, it is called butterfly structure. Butterfly structure. These 4 oxygen As peroxide leakage, 1 is oxide. See, 1, 2, 3, 4, 5, 6 bond with more electronegative oxygen here, plus 6, that is the maximum oxidation state. And this 4 1 minus 1 minus 1, due to this bond minus 1, due to this 0, this is minus 1, it is minus 1, and this is minus 2. The chromium oxidation number in CrO5 plus 6 that you got from the structure of chromium peroxide, which is bluish color and unstable. I'll take another component of chromium that you will get in the next block, K3CrO8. You can prepare this complex actually. In ammonia solution, any chromium plus 6 compound reacts with H2O2 will give this brown color complex. Actually, it's a structure you should write as CrO2 whole 4. Now, if you take simply oxygen with minus 2, then you will get minus 2, that means minus 16 plus 3 plus 13. It is impossible. Chromium maximum oxidation number plus 6. It has valence electron 6. You have to know the structure, or you can take oxygen O2 2 minus also you will get. If I draw the structure, see, it's a structure like this. It's structure like this. Very special compound of chromium. Here the counter ion is K plus, counter ion K plus, counter ion K plus. And see, 1, 2, 3, 4, 5 number of bond with more electronegativity. Here chromium with plus 5 oxidation state. Chromium. If I take O2 2 minus, then also 4 into minus 2 minus 8 plus 5 minus 3 and 3K plus. Then you got idea how you will get different oxidation number of different atom in a molecule, but the condition you have to know the structure of the molecule. I'll take another example from which you will get the oxidation number of different atom from their structure. Carbon suboxide, carbon suboxide. Carbon suboxide C3O2. The structure is C, double word C, double word C, double word O. C, due to this bond plus 2, due to this 0, 0, this is plus 2, and oxygens are minus 2. Very simply you got. From the structure it is very clear. 2 carbon with plus 2 middle carbon is 0. In JEE Mains we get question type. In which of the following, how many atoms with 0 oxidation number? There you have to know the structure. Otherwise you will not get 0 oxidation number sulfur. You know, ammonia polysulfide like NH4 whole 2 S5. This S5 2 minus is a polysulfide. S. Terminal 2 sulfur minus 1, minus 1. All are with 0 oxidation state. Medials are with 0 oxidation number. Remember this. And you know, Br308, a molecule Br308, from the formula you will get the average oxidation number of bromine. But individual oxidation number of bromine we get only from the structure. If I draw the structure, Br, this is the structure of Br308. This is the structure of Br308. This is, see, 6 bond with more electronegative, plus 6. This is 0. 4 bond, this is 6 bond. Total 16 by 3. If you do calculate by taking oxygen is minus 2, there you get average oxidation number of bromine plus 6 by 3. But I told you, oxidation number of an atom in a molecule never fraction. Individual oxidation number never fraction. Fraction will come just due to average. No other reason. Now, you will get minus half only in superoxide. You know, superoxide is O2 minus, never O minus half. One oxygen molecule when accept 1 electron, then it is O2 minus. There if you do calculate the oxidation number of oxygen atom, you will get minus 0.5 or minus half, that is real. But remember, O minus half never exists. O2 minus will exist. Like peroxide is never O minus 1. Peroxide is O2 2 minus. Now, You know, it is called H2SO5. H2SO5. It is a paracid of sulfur. It is called par-monosulfuric acid or Carroll's acid. Here the sulfur oxidation number you will get from the structure. If you do calculate oxygen by taking -2, your answer will be wrong. See the structure of par-monosulfuric acid. This is a par-monosulfuric acid. This is a peroxylic H. See here, 1, 2, 3, 4, 5, 6. That means 6 number of bonds with more electronegative oxygen. This is +6. These 2 oxygens with -1 oxidation state. Another oxyacids of sulfur you will get in your syllabus, that is H2S2O8, that is called per-disulfuric acid, or it is called Marshall acid. If I draw the structure of Marshall acid, you will get the oxidation number of 2 different sulfur. This is the Marshall acid. This is also per acid. There you will get peroxy linkage. This is the structure of Marshall acid or per-disulfuric acid. Here see 6 number of bond with 4 electronegative oxygen +6. Here also +6, and the middle to oxygen is -1. Remember, its salt is K2S2O8. Is abnormally powerful oxidizing agent. Due to this 2 peroxy oxygen, you will get an inorganic reaction. Remember, this oxidation number will give an important idea, very crucial idea to digest redox deicide in inorganic chemistry. Stay with us. I'll do discuss different applications of oxidation number in inorganic redox reaction. From there, you will get a clean idea about the redox reaction. Also, you will get a very clear idea about the equivalent weight. Thank you, students.